Okay, welcome to Module 8, where we're going to finish up Chapter 4. So we're looking at antiderivatives. So for some motivation, let's look at the problem of a body falling under gravity. So from science, you might have learnt that an object in free fall with no other force acting upon it, its velocity is given by minus gt plus v naught. Okay, so dx dt is the velocity, g is the acceleration due to gravity, v naught is the initial velocity, and time is t, and x is distance. And so if we solve this differential equation, that will give us x. So to solve it, we need to know which function has its derivative minus gt plus v naught. Okay, so let's work on it term by term. Now, we know the derivative of t squared is 2t. And so we want to get minus gt. So if we take 2t and multiply that by minus g on 2, this gives us minus g on 2 times the derivative of t squared. And working on the other term, v naught times t is the function whose derivative is v naught. And so just double checking, we've got minus gt squared plus 2 plus v naught t. Take the derivative of that, down comes the 2, cancels with the 2, we subtract 1 from the power, we get minus gt. The derivative v0t is v0. Good. But there's a problem with this answer, right? Because it doesn't work in all situations. What happens if we start at 100 meters up? That minus gt squared over 2 plus v0t has to be at 0 when t is 0. But then we just remember that if we add a constant to our function, this will not change the derivative. So our solution to our problem is minus gt squared on 2 plus v0t plus x naught. And x naught, you can figure what that is just by plugging t into the equation. It's the starting distance above the ground. Excellent. So this process of undoing the process of differentiation is called antidifferentiation. And so when we say that a function is the antiderivative of another function, so minus gt squared on 2 plus v0t plus x naught is the antiderivative of minus gt plus v naught, that means that minus gt plus v naught is the derivative of minus gt squared on 2 plus v naught t plus x naught. Okay. Now, remember, a function can have only one derivative, right? Because that's the slope at that point. But it can have many antiderivatives. Since all functions, fx plus c, are antiderivatives of the derivative of f. Okay? And that's true because if you take functions and just look at a whole bunch of parallel functions, they're going to have the same derivative because they're going to have the same slope. And that c turns out to be important because it allows us to solve the initial value problem, right? So given the derivative plus a starting point, which is like given the speed, you know the speed for all time and where you start from, you can figure out where the object is. And so we have our derivative rules, so that gives us our antiderivative rules. Okay, so we know the derivative of c is 0, so that means the antiderivative of 0 is c. We have a power rule, right? Because what happens when we take the derivative? Down comes the power and we subtract 1 from the power. Okay, to take the antiderivative, we add 1 to the power and we divide by that power. And you just double check that that works, right? Take the derivative, down comes the n plus 1, the n plus 1's cancelled, and we're left with x to the n. Notice this only works if n is not equal to minus 1, because we can't divide by 0. But that's okay, because we know that the derivative of ln of x is x to the minus 1. So that means the antiderivative of x to the minus 1 is ln of x. Great. So that means we can take the antiderivative of any power. Trig functions. Okay. Now this always causes a little bit of confusion because we remember that the derivative of sine is cosine and the derivative of cosine is minus sine. So that means the antiderivative of sine is minus cosine and the antiderivative of cosine is sine. So the minus signs get flipped. And we can do a little bit better, right? Because we know that the derivative of sine kx is k times cosine kx. So instead of multiplying by that k when we take the derivative, we divide by that k when we take the antiderivative. So the antiderivative of sine of kx is minus cosine kx divided by k. And we can just double check by taking the derivative and checking that we get back to sine kx. And the antiderivative of cosine of kx is sine kx divided by k. And again, we can double check by taking the derivative of sine kx divided by k, and we get back cosine kx. We know the derivative of e to the kx is k times e to the kx. So that means the antiderivative of e to the kx is e to the kx divided by k. Remember, it's the inverse process, so we just always do the reverse. And since the derivative of b to the x is ln of b times b to the x, the antiderivative of b to the x is b to the x divided by ln of b. Okay, so your module question for today is, what is the antiderivative of the constant m? Okay. So basically what we've seen is that every differentiation rule, run it backwards, you get an anti-differentiation rule. So for example, since the derivative of a sum is the sum of the derivatives, the antiderivative of a sum is the sum of the antiderivatives. It just works the same going backwards. Same with constant multiples. The constant multiple of an antiderivative, the multiple of a, the antiderivative of a multiple is a multiple of the antiderivative. Okay, and you can just double check that by just taking the derivatives and you see that you end up where you started from. There is an anti-differentiation rule for the chain rule. It's called the method of substitution. We won't deal with it in this class. You might have dealt with it if you've done another calculus class. Anti-differentiation turns out to be harder than differentiation because you've got to know it's working backwards from differentiation. We've got all these rules for doing differentiation. So it turns out there are some functions where you can't put it in terms of the functions that we know. A famous example is e to the minus x squared. If you look at the antiderivative of that, that turns out to be the normal bell curve, but you can't write it as a elementary function. Another example is cosine squared of x. However, even though we don't have formulas, we can still find numerical answers, right? Because, right, we're taking an antiderivative. That means we're given the derivative. So that means if we know the derivative, we know how things are changing, we can use the microscope equation. So that's Euler's method, is just using the microscope equation again and again and again and again, taking little steps. And so we can use an Excel file or something to find numerical values still. Okay. So let's finish off by doing some examples. What's the antiderivative of 5x minus 3? Well, the antiderivative of 5x is 5x squared divided by 2. The derivative of minus 3 is minus 3x, and I'll just throw in the plus c. What's the antiderivative of x to the 6th minus 8x to the 5th plus 22 pi cubed? Well, antiderivative of x to the 6th is x to the 7th divided by 7. Of x to the 5th, it's x to the 6th divided by 6. So we get minus 8 divided by 6. So that's why we've got minus 4 on 3. The tricky thing is 22 pi cubed. That's just a constant, right? So the derivative of a constant is just the constant time, that constant times x. So we get 22 pi cubed times x. And then we throw in the plus c. What's the antiderivative of 5 e to the x minus 3 sine 3x? The antiderivative of 5 e to the x is 5 e to the x. That's because the derivative of 5 e to the x is 5 e to the x. Antiderivative of sine is going to be minus cosine, so the minuses cancel, we get the plus. It's sine 3x, so we're going to divide by 3, so that cancels out 3, so we just get cosine 3x. And again, I just throw in the plus c. That plus c is important if we try and solve an initial value problem. So here's one. Find L of minus 2 if Lx is a solution to that differential equation with that initial condition. Okay, so if we've got y prime equals e to the 2x, the antiderivative is e to the 2x divided by 2 plus c. Okay, we can use that c to solve for the initial value, right? y0 equals 1 equals, or e to the 2x, well, e to the 0 is 1, so that's 1/2 plus c, so c equals 1/2. So therefore, L of x equals e to the 2x plus 1 divided by 2. Plugging in minus 2, we get that the answer is e to the minus 4 plus 1 divided by 2, which is approximately 0.5092. And we'll finish by looking at question 6, because I'm giving you that for homework. So question 6a, this is a question on oil consumption. So for homework, you will be completing the rest of this question. The rate at which oil is consumed grows by 5% each year. Let R be the rate of oil consumption per year. Solve R prime. Well, okay. So if it grows by 5% per year, that's constant per capita growth. So that means we have the differential equation R primed equals 0.05 R. We'll let R0 be 1. So we're just using today's rate of oil consumption as the base. So like if R equals 2, that means we're using twice as much oil as we're using today. Well, that's an easy differential equation to solve because it's just exponential growth. The solution is R equals e to the 0.05 t, right? Because you see, you take the derivative of that, down comes the 0.05. So satisfies R prime equals 0.05 R. And if you plug in 0, you see that you get 1. So that is the solution. So starting you off on part B, that means we're looking at the differential equation y prime equals e to the 0.05 t. So taking the antiderivative of that, the antiderivative of e to the 0.05 t is e to the 0.05 t divided by 0.05. Well, that's just multiplying by 20. So it's y 20 times e to the 0.05 t plus c, because we can always throw in that constant of integration. That's what they call it, the constant of integration. Okay, and you will complete that in your homework. And that's where we stop.